Good morning or good evening, wherever you are. I am presenting this talk on behalf of my student and collaborator. Essentially, this is work that started when I was at the University of Auckland, and Tiago is a student there. He's just finishing up. But since he happens to be currently in a time zone that's too early, he's actually in South America, back home, because of COVID, so I'm doing the talk. Okay, so what we are talking about here is common sense reasoning and deep learning for transparent decision making in robots to provide some longer term perspective. So this is the set of research questions we started with. This is something that I was doing some years ago. And so this is to say the questions that motivated research over the last 6 to 7 years. And so the thing we said was, how can we get robots? And this is strongly motivated from the viewpoint of a cognitive systems and robotics person. So how to get robots to represent and reason with different descriptions of knowledge and uncertainty. And because this description is going to be incomplete and potentially inconsistent, how do we get these robots then to learn, say, interactively and cumulatively, not just incrementally, over time? And the last bit, which I will probably focus on more today, the second and third bullets, is how do we get designers to understand the robot's behavior and establish that it satisfies certain desirable properties. And here is where we get to this notion of explainable agency, intentions, goals, and so on. Right, so this is where I'll focus. So to just again provide a sort of perspective, I'm going to come back to underlying representation, and this is based on the the push that representation is the key to reasoning or learning that comes after, or explainability. I want to say that this work is motivated primarily by the notion of a robot assistant, right? And in this work, I will talk primarily about sort of a robot doing, say, tabletop tasks, or a robot moving around in a map of the world, right? But we have also looked at other instances where it is more about doing computer vision, scene understanding problems. But I will not get into that much here. Okay, so the underlying architecture is that of this refinement-based architecture. This is a joint work with Michael, Shuchi, and Jeremy. And this started with Shuchi's work as a PhD student with me. This was 5-6 years ago. And now it's evolved to something like this, to say that, again, motivated from cognitive systems, is to say that systems that represent, reason, and learn do so at, say, different levels of abstraction, and use different mechanisms potentially. They just have a nice way of communicating between these different representations. So in that context, we can think of this agent or robot to internally have this logician, statistician, and an explorer. And I will primarily in this talk be focusing on this sort of explorer bit of things, of doing this learning and trying to also provide some explainability. But as you can see from this picture here, it is sort of bringing into play things like non-monotonic logical reasoning, probabilistic execution. But if you're interested in that part of things, I encourage you to look at this paper. Okay, so what is the motivation here? Is to say that these days, these deep networks seem to be used widely in AI and robotics. Oftentimes, that's sort of like another thing that people use, even if they don't know whether it will do well or not. But there are some obvious limitations in the sense that you need large labeled data sets. There is this issue of coming up with computational resources to deal with them. And especially if you are dealing with, say, a robotics domain, oftentimes you don't have either one of them, large labeled data sets or sort of considerable computational resources, such that you can somehow process all this and work in what we call real time. And what happens also is, like, when you deploy these systems is you want to try and understand or interpret the underlying representations and reasoning mechanisms, right? And that is one key motivation here. And that, though there are a lot of people working on this, there is still a lot of unexplored or unanswered questions on how to do this with deep network architectures. The inspiration that we take here is that from that of cognitive systems, right? And the idea here is representation, reasoning, and learning. These are not different components that somehow coexist, but they are actually tightly coupled. They inform and guide each other. And this precise thing of sort of like, a fact of them informing and guiding each other is what we want to use. And we want to try and make each of these individual capabilities better, right? And we do so by, in this talk at least, we say that we are going to do both interactive and cumulative learning, and reason with common sense knowledge. And in this context, we want to use principles of relevance, persistence, and that should hopefully be clear in a few slides, to bring the notion of explanations, right, to try and explain things. And in terms of experimental domains, what I will be talking about here is simple domains motivated, as I said, from robotics and scene understanding. So to talk about occlusion of objects, stability of object structures, how do I sort of go about rearranging the scene such that I minimize clutter? And in other work, we've also looked at trying to answer explanatory questions, right? And with all this notion of explanation, the term being thrown about so much, I think it's important for me to at least say what is the scope and what are the underlying claims. And this again comes from, say, the cognitive system side of things. Is I need to lay out what I mean by this and what are these underlying claims for representation and reasoning. So when I say explanations here, I'm talking about relational descriptions of the decisions that the robot makes, plus say the rationale behind it, the beliefs that underlie these decisions, and the experiences that led to these beliefs. And I want to do so in the context of, or in terms of the attributes of the domain, attributes of the agent or the robot, and say the actions or other things that the robot is capable of doing. And in this talk, again, I'm going to say I characterize explanations in terms of, say, the level of abstraction, the level of specificity, and the level of verbosity, and try and provide a general methodology to construct these explanations. And the reasoning system, what it should do is it should be able to take these principles internally. And this is the claim I'm making, is it should be able to provide contextual information that is relevant to the task or the question that the human might have. And the humans, therefore, have this right to interactively determine the point along, say, the axes that determine the space of explanation and try and answer different kinds of questions, right? The robot should then be able to answer different kinds of questions. And the focus of this work is thus on using knowledge representation, KR tools, for transparency in reasoning and learning in systems that do both in a nicely coupled way. And I will not be here discussing human subject studies. I mean, we had this excellent talk before, and there are ways of doing this, and we are doing this, but I'm going to keep this out of scope for this talk and paper. Okay, so before I get started in the explanation, what does the underlying reasoning and learning system look like? So to do that, we created a sort of example. So we basically said, let's say you're going to do this notion of trying to come up with the occlusion of objects and stability of object structures. Say there is a robot manipulating with a human objects on a sort of like flat plane, and it has to do this. It has to basically try and decide occlusion of objects, stability of object structures that are stacked one on top of the other, and say be able to explain this. So let us first look at the reasoning and learning system. What would be a sort of vanilla way these days, at least, of doing this? Would be to say, throw some sort of deep network at it, the blue box on the left, to extract some features, and then throw another sort of deep network at it, which is the green box on the right, and say, okay, now I'm going to use these sort of combinations of a deep networks and or a deep network architectures to come up with some labels that tell you, given these input images, whether these structures are stable or whether these objects are occluded. What we instead want to do is we want to sort of look at the complementary strengths of non-monotonic logical reasoning, deep learning, and decision tree induction, and set up a reasoning and learning system that on the fly also extracts certain statements about the behavior of the reasoning and learning system. And let me again say that this is not one of those instances where you sort of take the deep network back project and try and figure out which nodes were used or which nodes were contributing to the answer. There is a lot of excellent work there. Here, we instead want to sort of bring out a certain understanding of the behavior. And we, as I said, because given our claim that we're going to come up with these relational descriptions, that's what we want as the output. Okay, so what is the input? As the input, what we have is we have these RGBD images, right, or RGB images of objects and scenes, and we have both real world and simulated objects, images, depending on the application. And let us say someone gives you some labels to start off with, say to talk about object occlusion or stability of structures, right? So I would then go around and extract some geometric features and other sort of like object attributes, right? And this would take the form of, say, spatial relations, like what is above, below, left off, right off, and so on. And there is a lot of work to do here. And the key thing here is to ground these prepositional verbs, right? What does it mean to be above, below, and so on? And we have a paper in IJCAI a couple of years ago talking about how to do this on the fly. But let us say that we have extracted these features, right? And as I said, the traditional way of doing this would be to take these features, run it through some deep network that then learns the input-output mapping. Given these input images, it tells you whether the objects in there are stable or they are being occluded. But instead, what we say is we want to then not do direct this, go back to this deep learning system, but instead we say these extracted features, and I have some incomplete knowledge about the domain, right? I could have some, from the standard logic terms, I would have some basic sorts, some statics, fluents, and actions, and some axioms. And in this case, we use answer set prolog, and we say that if I had some prior knowledge, if I knew, for instance, that if I put an object down, then object A is on object B, right? Or if I know, for instance, that if one object is above another, then the second object is below this one, right? Basic rules of the domain or basic rules of physics, right? So if we can encode some of these, can we ask and answer some questions about object stability and occlusion? And if we can, that is where we stop. We say, no, no, we're not going to do anything more. We have found the answer. But if we are not able to, we use the same knowledge that is encoded to say that if I'm talking about object stability, I know what kind of relations matter. And I'm only going to look at those features and therefore those regions in the image. And I'm going to only train my deep network on those particular sub-regions, if you will, or regions of interest, ROIs. So what this does is it highly simplifies my learning process, right? So, and then I don't stop there and I say, okay, in addition to this, when I'm sort of using a deep network, I'm in some sense accepting that my reasoning system is missing some information. So therefore, any examples that I run through my deep network, I'm also going to use the same guys, the same examples, to try and figure out if I can find some equivalent rules that by decision tree induction, again, very simple, very sort of classical knowledge representation and reasoning tool, and to say, can I sort of extract some rules that will sort of mimic the behavior of this deep network? Again, not trying to understand which nodes contributed. We are here trying to say, can I understand some rules that mimic the behavior of the deep network? And if I do, next time around, can I then not use the deep network again, or not have to train it again in similar examples? And this again is a very simplistic, small subset of a decision tree that is very quickly learned. In this case, it's basically saying, for instance, that if an object A is above object B and B happens to have an irregular surface, you should be careful. It's probably not likely to be a stable structure, right? And you learn these kind of rules and add it on. This is a constraint. We can also learn other kinds of things. Now, let me do a quick sort of slides of saying, how does all this help come up with explanations, right? To do that, we said we're going to consider some question answer types, right? And we're going to pick some just as an illustration. It works with other types as well. But here we said, can we get the system to describe the plan? This is again motivated from, say, research in, what should this called? XAIP, yeah, explainable AI planning, is to say you need to be able to answer some kind of questions if you're doing a reasoning system, which is describe the plan, tell me why you chose a particular action, why did you not do a particular action? And why did you entertain a certain belief at a certain point in time, right? And so that is the components on the right of this dashed vertical line that you see in this thing. And the one on the left side is the sort of part that I have been showing you so far. And so what it does is we wanted to retrieve relevant information on the fly, say that if I want, and this comes naturally because you have a system that is encodes things logic in a sort of non-monotonic logic scheme. So therefore it's easy to pick things that are relevant and to, and there is a sort of set of methodology that's described in the related papers. I'm not going to get into that here. But then what it does is once you get the relevant information, you can very quickly answer these kind of questions. And in addition to that, we also put in this notion of a proof tree, like, belief tracing, especially for question types 3 and 4. So for instance, like, again, this is a short snippet. If someone were to tell you that a particular action was not chosen at a particular time, you can trace back and say what beliefs and what axioms led me to this decision. And by doing so, you can quickly put these together into a structure that can then offer a notion of explanation, given that we want it to be a relational description. And that is exactly what we do for certain kinds of questions. Whether it were a particular, especially for 3 and 4 here, if you were to talk about why not a particular action or why you entertained a particular belief, you would trace back in this tree, or you would create this tree on the fly and say that what sequence of, say, axiom execution and, say, belief propagation led me to make this decision. And I use that as a means to provide the answer. Okay, so let's see an example or two. So let's say that your goal here, take the picture on the left, and this is from this Baxter looking at a particular scene on a table in front of it. And it basically says, like, the goal was to move the red block. If you notice, that's at the bottom here, hiding behind this tennis ball, on top of the orange block. And what would you do? A reasonable approach would be to take the blue block off and then take the orange block off and then put the red block on the orange block. So if you were to ask, why did you pick up the blue block first after, say, the robot has executed this plan? So it would say, for instance, in this case, that had to pick up the red block and it was below the blue block. And if you say, why did you not pick up the orange block first? It would give a reasonable answer to that as well, saying the blue block was sitting there, my friend, I couldn't do anything about it. And then you could ask hypothetical questions as well. You'd say, what would happen if I push the ball, right? And it would sort of try and tell you what would happen based on its understanding of the domain and its physics. You can go a step further, right? Because it is tied into this architecture that reasons and represents at different resolutions, you're able to now ask it to provide more or less information, be more verbose or be more specific or less specific, or provide more details. That is like, a finer granularity of abstraction. So this is again another example that I just put on the slide to say if a robot is moving books between different locations, you can ask it to describe the plan. and then say, oh, I want more detailed information. So instead of talking about just room labels, it now starts talking about regions in those rooms. And then it can ask, you can also now ask questions at different levels of abstraction. It's able to dip into that particular representation and quickly pull out the information that you need. And just a slide
Mohan,
of
you should come to an end soon.
this is the last but one slide in essence.
Okay.
So I'm almost there, right? So I'm just going to run through this one thing here to show that because it is a system that does reasoning and learning together, it is able to, over time, like if you look at this precision and recall standard metrics, here we are trying to see if am I retrieving the relevant literals to come up with a useful answer, where the ground truth is provided by a human. So without these axioms that it has learned over time, it has a poor value, but after time, over time, it quickly ramps up and gets up a really high accuracy. Okay, so I'm going to summarize here and say what I briefly talked about here is a system that represents reasons and learns jointly with different descriptions. And this in different papers we have shown simplifies design, increases confidence. And this particular talk, I briefly talked about the combination of non-monotonic logical reasoning, learning and inductive learning and deep learning, such that they inform and guide each other. And you learn these axioms that describe the behavior of the system. And also we are able to provide interactive explanations. And in the future, we are looking at exploring further the interplay between reasoning and learning. I'm done.